and he came to APS for 5 years. Slightly less than 5 years.
Slightly, yeah.
And then he went back to SLAB. And now you are in charge of Xfel?
No.
What are you in charge of?
They don't trust me.
I think Jerome is in charge of Xfel fingerlings.
R&D.
So we are happy to have him here for the lecture on basic principles of the electron data.
Okay.
And why at the
Maybe
at the same time, Ryan did his PhD in Berkeley. When was it? 4 years ago? 3 years ago?
2007 I graduated.
2007. While in Berkeley, he also taught at San Quentin. Do you know where San Quentin? It's the most notorious prison where Al Capone stayed for. And did you teach mathematics there?
Yeah, math and math.
So after that, he came to Oregon as a so-called director's postdoc, which is very prestigious postdoc. And ever since he's started at Oregon. Okay, so that's the slide.
Let's start. So yesterday, Kwangje gave the time domain treatment of one-dimensional FEL equations, and they introduced this very important row parameters. And actually, that's one of the most important parameter for FEL. So we'll repeatedly come back to this row parameter. And there was in the yesterday's lecture, Kwangje talked about this. We don't need to know the detail of the microscopic electron distribution, and he averaged over this delta t, the sort of time slice. And this delta t is not well defined. What exactly delta t is. So there's some ambiguity of how you treat that, and what delta t you should take. So in today's we'll start going to the frequency domain. So if you do a Fourier transformation, it's automatically integrated from minus infinity to plus infinity in time. So there's no ambiguity what time you should be dealing with. And it turns out the equation is also, the Maxwell equation is simplified in the frequency domain. So that's what we're going to do here. So first thing we introduce, we make a Fourier transformation, right? So yesterday we have this E.
Change the pencil. This erase mode.
The erase mode, yes. Yeah. So let's introduce this. This E tilde from yesterday, right? E tilde ZT is a slowly varying electrical field. So the fast dependence is EI kz minus omega t. That's already taken out. Let's write this as okay. So now we introduce E nu z, right? The E zt now become E nu, the free component of the field at a particular z location z, and because the E is already slowly varying, so the variable nu is omega minus omega over omega 1. Delta nu is nu minus 1 equal to omega minus omega 1 over omega 1. So delta nu is the relative frequency change. Equal to k minus k1 over k1. So this is just definition Fourier transformation. Okay, and with this, when we go to the Maxwell equation, let's see the equation. We go in the 1D. So if we now go to equation 3.6. That's the Maxwell equation, and we put this this form of so put this into this. So in the equation 360, we have the 1D Maxwell equation, right? dt. So now it's now we should put it in the this is Ex minus epsilon c dj x dt. Okay, and the Ex, you can write Ex as E tilde ct e I k1 c minus ct. Oops. Okay, so that's Ex, and now you put the Ex. Now you put you put this form in there as well. So the whole expression is d nu e I nu k1 c minus ct e nu c. Okay, and okay, so when you differentiate with respect to t twice, the second derivative, you'll get something in this. So you differentiate you operate this on this form here, right? You'll get I nu minus c. You get t here, right? You differentiate this twice, you get this square. Okay, and if you differentiate the z with respect to the face here, you'll get I nu k1 square, right? Because they're different by minor sign. So if you just operate on this face for this whole operator, they cancel, right? Because they satisfy the wave equation here. So what's left is so what I'm saying is the second derivative with respect to z to the face cancel with the second derivative with respect to t. Okay, but what's left is the second derivative with respect to e, the slowly varying part. So the slowly varying part, you have this. There's two. So what's left is the minus. And E I U K1 C. Okay. So the t part is already taken care of. So I'm now focusing on the z partial derivative with respect to z on this here, and for this, if you there will be okay, and then you have 2 times, let's see, 2I mu k1, I guess. Yeah, okay. Okay, let's just write them down. So the t differentiation is I mu k1 square, and then minus, and then so when you operate this on this twice, you operate this on each of them. And then you get the cross term is 2 times, and then you operate this on this face twice. You get I mu k1 squared. Okay, e mu here, e mu here. Okay, this what I'm saying is. This term cancel with this term here. The second derivative with respect to t cancel with second derivative with respect to z for the phase. So what's left is this term. And under the spirit of slowly varying approximation, we say we use approximation that the d nu dz is much less than k1 mu. So we can ignore this term relative to this term under this approximation. Okay? So this will be also, so this cancels, that cancels, this will be set to, this will be neglected. So all we left is this term here on for the right hand side for the left hand side of the Maxwell equation. Okay, so the right hand side you keep it down. So what do you end up with? So is this equation here, d nu. Okay, so there's a minus sign, but there's a minus sign on both sides, so they cancel. Right? So then we do the inverse transformation. Okay, so we do the inverse transformation. We get 2I mu k1 Okay, so we from here we inverse transform to here. And then you have to remember, you have to put in the definition of J. Jx is a transverse beam current. And that's leading to, Jx is Vx dot the electron line, the electron the density, right? And the electron density, we write it in, I think, let's see, Jx is given somewhere over here. Okay, so Jx is given in equation 3 point, so now, so remember Jx in equation 3.61. Okay, if you go to the lecture notes, page 87, equation 361. So you put in the definition of Jx into this into the right hand side, and this will give us okay, it's a little bit long here. There's a cosine term, right? Cosine KUZ term. And the 2 pi sigma x squared gamma. And then there's a sum of this delta function. I don't have space, but it's in the notes. Okay, so, and now you see by doing this Fourier transformation, now the t is just the integral from, say, minus infinity to plus infinity. Okay, so, and then what we did actually, how we get here, we have to also perform an integration by parts. So the d dt, right, if you integrate by parts, become a d dt on this term with the minus sign. And that's with the minus sign, that brings down this I nu k1. Okay, and then the integration in doing integration by parts, we assume the electrical field vanish, and also charge density vanish at minus infinity and plus infinity. So there will be no, there's no boundary term. So that's what's in the approximation here. That's why this approximate sign. And also we take each particle should have its own gamma, right? This is a sum over particle, but we say we are dealing with a beam relatively monochromatic in energy, so we put some gamma. Let's say we call it a gamma resonant. Yeah, we put in some central gamma of the electron beam. So this equation in the frequency, Maxwell equation in the frequency domain is much simplified after the slowly varying approximation. And on both sides we can cancel this I nu k1. Okay, so the equation get further simplified. There is, I think the 2 also gone, so there's so 2 got moved to 2 pi. There was a pi, now we moved to 2 pi here. Okay, then the next step is in the delta function we have the delta of j equal 1 to n, and the z minus z j t And then we like, remember we introduced this theta variable. Theta is the electron's phase relative to the plane wave. And the theta, so we want to change this into delta theta minus theta j. Okay, so to do that we need to, so going from, so theta is K1 plus KU C minus CT, right? That's the definition of theta. Okay, so by doing this, we further simplify the frequency domain of the Maxwell equation. So after this substitution of variable, d e nu dz equal to minus ek. Okay. Okay, let's first write it down. Okay, so this is the equation 3109. How do we get here? So there's a few steps. If you we have in this equation here. So in this equation we have this here and okay, this is minus here, right? Okay, we have this. We have to combine this into this theta term. The way we did, so the way this is done is so we say okay, this is the end result, but I want to just say a few words where this come from. We have this cosine KUZ, which is 1/2 EI KUZ plus E minus I KUZ. There's also JJ factor. I'll first write them down. Okay, and then we have to combine this phase with this phase here. So this phase is E minus I nu K1 C minus CT. So I'm just trying to collect all the term with the phase with the phase term. Okay. And when you combine them in here, right? For example, you have E. Let's there's a two term, E I K U C minus I nu K1 C minus CT and plus E minus I K U C minus I nu K1 C minus CT. Okay. There's a factor of 1/2. And this term here is almost E minus I theta. So this is almost E minus I3. Remember, in frequency domain, I have to keep my nu. Nu is the frequency relative to the fundamental frequency. Nu is equal to omega nu is omega over omega y. So in frequency domain, you get rid of t, but you have to keep nu. Okay, this is almost I nu theta 1, theta, right? Because the definition of theta is here, right? I times nu here, I got a nu ku k1. There's a ct c k1 here. Oops. This is almost minus I nu theta, but then but it's not, because this I have to say, I have to put this as a nu. I have to make a so to make that a e minus I mu theta, I have to times mu. I have to times mu here, and then I have to take it out. Right? So I instead so the original equation I have minus I ku z, right, which come from here, right? Come from this here. And then I want to make this combination. So I make this I insert a minus I mu ku z here. By inserting this, I have to take it out later. So I take it out with this term, and then my original term is this. So what I end up is I got e minus I mu theta, but then I also got another term, which is here, right? Which is I nu minus 1 ku z. Okay, and that term, this is by definition, this is delta nu. So there's and it turns out you have to keep this term. We'll talk about that. So you get so you see that by doing this, we can go from this t variable now goes to ei minus I mu theta variable. Okay, and what about this term? It turns out, I think Kwang-Jie must discuss this yesterday. For undulator with large k, the longitudinal motion is actually not uniform. There's this when the electron wiggle in the undulator, the transverse wiggle also introduce a longitudinal velocity oscillation, which is at twice of frequency of the transverse undulator frequency. And then, so really, what we should do is take some average t, and then there's some fast oscillation term on top of this average t. And if you do it properly, then there's you have to take that average into account. By doing this proper Wiggler average, you will have something for this term. You have some associated with J0, k square over 4 plus k square, like this. Okay, and in this term, so this term looks like it's not a resonant, right? Because this is if I make this an E, I can make this E 2I KUZ, E minus I KUZ, and minus I nu K1 C minus CT. I mean, this looks like this, but this is fast oscillatory. But then if you take into account that T also has some fast oscillator part, and you make a proper average, so this here will give you minus J1 k square over 4 plus k square of E minus I nu theta, and then E I delta nu KUZ. Okay, so this is plus. It's a little bit dense. So I'm saying the second. Let me group it for you. So I'm saying this. This manipulation give me this J0 times this factor, and this singular manipulation here will give you will give you this term. And when you combine them, okay, you combine this, you see there's a common factor is E minus I mu theta times E I delta mu ku z, and then combine this two combinations. This is J0, this is J1. These two combination give you this Bessel function factor Jj.
Well,
Yeah.
give me one more explanation for why we have J0, J1 there.
Okay, yeah, so the explanation is this. So when theta is equal to, we define this, right? K1 plus Kuz minus Ck1t. But the t is because longitudinal velocity is not a constant. So t has a sort of, I can write t. Yeah, it's right. Okay, I can. T has two parts. T has a t average. I think probably it's in somewhere. Kwanje, did you cover this? The Bessel function factor?
3.71.
Huh?
3.71.
3.71.
As I said,
Oh yeah, that's right. 3.71. Yeah. This is a subtle point, right?
yeah, I just said they have to work it out themselves.
Okay. So let's just illustrate the steps and you work out. Yeah.
But
So
the prof didn't work it out.
yeah, you didn't do the homework last night. Okay. So so T has a, okay. You look at the equation 3.71. Because the longitudinal velocity is not a constant, T has two parts. There's an average T, and then there's this k squared over omega 1, 4 plus 2k squared sine 2k uz. Okay.
So the theta.
Theta is really should be defined with respect to this.
Yeah.
And then when that's the case, so you define, so the proper definition of theta is this, okay, and then you have to substitute the real t into this, and then you get an oscillating term, and then you get an oscillating term in phase, and the average of that naturally leads to this Bessel function. That's a mathematical steps.
Theta is only average time.
Right.
T bar.
Right. And the reason we can do this average, right? The average, you see, the oscillation happen on the scale of the undulator period. The reason we do this average is in the spirit of this slowly varying approximation. We assume this slowly varying electrical field does not change per undulator period. So the gain process happen over many undulator period, which you have to check. So this is an assumption at this point. But if you solve the equation, and indeed the gain happens over, like, say, 100 period of the undulator, then this is a self-consistent approximation. Okay, so there's some math involved. I hope I covered the major steps. Okay, so the main equation we're getting at is this here, and it's rather simplified. Right, it's just a simple, derivative with respect to z, and the t integral. There's, because of Fourier transformation, we changed the t integral to theta integral, and the theta integral you can go from basically minus infinity to plus infinity, and this is if you write this out, it will give you e minus I nu theta j, right, for each of summation. So this is like this bunching factor, but it's a more rigorous way of writing this bunching factor. Okay, so another point is this term, right? This term, see the nu minus 1 is pretty small because we expect nu is close to 1. Nu is close to 1, nu minus 1 is a small number. But Ku times Z has to be large, is a large number because Z is, again, we say we expect this is slowly variant. That means, we really have to go many undulator period to see some changes. So that means KUZ is 2 pi, number of undulator period is a large number. So a small number times large number is indeterminate. So you have to keep this term. Maybe one more, let's just go one more step in this direction. So it turns out it turns out for future development, we don't like this term on the right hand side. So it's just the convenience, okay? Just we redefined. So instead of E nu tutor, right? We keep you. I think we use the tutor here. We redefined another variable E I delta nu K U C E nu. We get rid of this tilde here, but by applying this phase here. So if I do this, so basically, what I'm doing, I'm moving this term over to this side. Okay, I just for convenience, I don't want this term to be on my right hand side. I move it here. Okay, if I move it there, I have okay. In the previous equation there, I move this to here. Okay. And that equal to make sense? Okay, so if I define this, so I just make that this is my definition of E nu without the tilde, right? This is definition. If I plug this definition into here, this is equal to this. Okay. So in this, by making this change of variable, the Maxwell equation now 1D is now given by So it's the same. Okay, so I'm just trying to clean up the right side by moving the phase vector on this side. So I redefine E nu. Okay.
I think there is no G in I WQ.
Which one here?
G. So G should be this
Oh,
one.
the Z disappeared. Right. Thank you. Okay. Okay, so we have an unambiguous way of writing down the Maxwell equation in the frequency domain. So now we go back to the equation motion, right? We go to the we want to write down, Pointier derived this pendulum equation for equation motion, and then I think he introduces a collective variables approach, because you have many electrons. You can, it's difficult to unless you do simulation, it's difficult to solve electron by electrons. So in the simplest case, there was this collective variable approach. But in this, now we want to introduce a distribution function for the electron, and then the distribution function should follow the equation motion, and we solve that distribution function together with electrical field. So that's now we go to this section on this kind of distribution, because it contains all the delta function to represent the electrons, to represent the shot noise of the electron, and we call this Klimatovich distribution function. So now we introduce the Klimatovich. I mean, it's basically just, imagine you have this phase space. This is the phase space variable in 1D. We are using theta as a longitudinal bunch coordinate, and the eta is the energy variable. Okay, and then you have lots of particles, right, in this phase space. You have, each point is a particle, okay, and we introduce the distribution function f, and this distribution function can change from one z location to the next z location. So this distribution function is theta, and the independent variable is z. And we use K1. We chose some particular normalization. So each point is located at the theta, say this point located at theta j, and so each point is a delta function there, and you sum over all the points, you get your distribution function. And then the theta j and eta j will evolve by the equation of motion, which is a pendulum equation. The normalized I is the peak current. I is we assume in the theoretical treatment, we assume the beam is a flat top beam. So I is just the current of the flat top. I over EC is the line density of the electron. And so really, maybe I should, yeah. So we in order to let's see, so the F contains the average of the electron distribution, but also contains this granularity of the electron's shot noise. So we write it in a way. So we write it the smooth part. So we say the beam is long in theta. So it's really almost in theta dimension it's almost independent of theta. But it has some energy distribution, and the energy distribution we call it V theta. And then the rest, anything deviating from this smooth distribution, we just lump all of them together. We say it's a delta F. Okay, we just separate it. So this will be the smooth part. Smooth. And this will be the sort of sharp noise part. Plus any, micro bunching. We can think it that way. Okay, the normalization is chosen. So if you integrate this over, okay. So if I integrate this, so this part, so because it's chosen, this is sort of the average. This part is supposed to be, it's just deviation from the average. So the integration of this part is 0. So the normalization, if I integrate the F, so if I integrate this over d eta d theta, I would get, if I integrate this over the phase space, or the phase space here, I would just get n times k1. Right, I integrate over the phase space. I pick up all the particles, and there are n particles. I over EC. And that I claim is K1 basically times my bunch length, because this is the total number of particle. This is the number of particle divided by the bunch length. Roughly, it's a line density. So this is roughly LB is my bunch length, right? So n cancels. So this is K1 times LB. Okay. And then if I integrated this over d eta d theta, I would get a V8 D8. Okay, because there's no theta dependence, so this is a d theta. The theta, there's no in this part I have no theta dependence, so the d theta is just integrating from again over the bunch length. So over the bunch length in the units of wavelength, wave number. So remember, theta is let's say from 0 to theta b, where theta b is the bunch length in units of wave number. So it's again like just this, right? So the integration of this is also what I call theta b, which is K1 LP. Okay? And this one, if I integrate this one, because it's a fluctuating part, and this one is deviation from average is 0. So what I'm trying to say is that this normalization was chosen. You see, if you make this has to be equal to this plus this. If you make this equal to this normalization is chosen such that right? That's a normalization. So we chose the normalization. The distribution over the V is the function is the distribution over energy. Integrate over energy, we get 1. That's a normalization for this particular choice. Okay, so yeah, keep in mind of this normalization, and then we have let's see. Okay, now so similar to Maxwell equation, we introduce a frequency representation of the distribution function. Here is now this is distribution function in theta, eta, and z. But just like what we did for the Maxwell equation, we integrate the theta is basically t, right? We Fourier transform from theta to nu. So that's just to usually the equation is easier to solve in the frequency domain. That's the approach we're doing here. So now we introduce now frequency treatment. So F nu eta c equal to 2 pi. That's just the definition of what's F nu. Okay, so we just define the frequency Fourier transformation of F as this. Now you plug in remember the delta function for F, right? F is a bunch of delta function. It's pretty hard to solve that. So first thing we did is a Fourier transformation. Then it's try to simplify that. Remember, F is a delta theta minus theta j. So delta theta minus theta j, when you integrate over d theta, you get E minus I nu theta j, right? Because the delta function, you collapse the delta function, but you still have the delta in energy. And now we just use this notation here. So the front is still K1. Oh, I see. K1 2 pi I over EC. right? The 1 over 2 pi is by definition here. So K1 2 pi I over EC is 1 over lambda 1 I over EC. And the I over EC is the line density. Time we just call it n lambda. It's the number of electrons within one wavelength. Right? So that's just n lambda. Okay, so now, so now with this F nu, now if we look at our Maxwell equation here, okay, we have this same factor E minus I nu theta. If you integrate over d theta again, okay, maybe just write it down. Now this part you can also simplify, right? It's K1 2 pi. The d theta integral is easy to carry out with the help of delta function. Okay, so the sum is okay. So now I look at my Maxwell equation is here, and that's just this is basically the F nu. Oh, this okay. This is basically F nu theta z d beta. Okay, we have to sort out the coefficient in front. So the sum, this factor E minus I nu theta j, the sum of the phase, the sort of so-called bunching factor, is now just related to this, right? If I do another eta integral, this will disappear. So then I'll get this, which comes into the right side of the Maxwell equation. So now I make a connection between this distribution function and the Maxwell equation. So the now Maxwell equation, the 1D, the Maxwell. Now the constant we group it into kappa 2 and E. So the back here. So we know this Maxwell equation is driven by the transverse current. The transverse current depends on this in this theta variable depend on this this phase, the summation of this phase, and this summation of this phase is just simply the distribution function, the frequency domain distribution function. Properly integrate over energy. So that's just the connection between the Maxwell, the electrical field, and the distribution function. And the notation is kappa 2 as defined before. So kappa 2 is ek, the JJ factor, over 4 epsilon gamma r NE is current divided by EC times 2 pi sigma x squared. And this is just the electron's volume density. I over EC is the charge, is the line density. And the 2 divided by transverse cross section, we get the volume density. So, okay, so this is a, so we made a connection now between the 1D Maxwell equation and the distribution function we introduced in the frequency domain. Okay. So the next step is the distribution function follows the equation motion. So this is a so-called the continuity equation, right? If you follow the electron's motion, the electron's density doesn't change. So the continuity equation for so F, this is the total derivative of F with respect to Z is given by the partial derivative of F with respect to Z plus the partial derivative with respect to theta, and the d theta dz plus df d theta. This is equal to 0 if you follow the equation motion. So that's just by this Liouville theorem. The phase density doesn't change if you follow the motion.
I'm sorry, I missed your step.
Previous, okay.
Okay, a little bit.
This one.
Yes. What did it K1 disappeared? K1 above there.
K1.
One is right hand side.
Here?
Yeah. But bottom there is K2.
Okay, I see. Let me see.
K1 over there.
You
Yeah,
mean this K1
K1
here?
Yeah. There is lambda, n lambda, then it disappears, but so lambda n is not being used. So, then all of a sudden, K2 is showing up. That
Right, you mean this is kappa 2, but this, where's you're saying where is K1 here?
Yeah. Where did it go?
It vanishes in the definition of F mu, right?
Right, yeah, okay. Hold on. No, F, right.
Somewhere, okay, roll off.
So it's let me go back. I think I think yeah. So you see here,
Yeah,
right?
all right.
I need in order to get F. So this I went a little bit too fast. So this equal to, I have to write this into K1 over IEC. I don't know, even 2 pi, even 2 pi is needed. All this, I needed this combination, okay, to give me this, because that's my F nu, right? So so I need, so this all being combined into called F nu. But then I need to compensate with this factor. Okay. Yeah. So that's I need. I then this factor. So this whole thing got combined into this. And then I have I over EC over 2 pi sigma x squared is now appear in here,
Okay.
and that's called this. And then and then kappa 2 is the whatever the rest.
Okay.
Okay, yeah, there's some redefinition there. Okay, thank you. Yeah. Okay, so that's the Maxwell equation, and then we try to write down complementary equation for the distribution function. That's our goal here. The complementary equation is this a continuity equation, and by following the equation motion, we have this we guarantee this total derivative with respect to f is 0. By following the equation motion, meaning we have to d theta dz has to obey the equation motion, which we derived before. And remember so I should use the total here. So d theta dz is 2 ku eta. D eta dz is we have this kappa 1. Oh, yeah, we have. So let me write it down first. D mu. Plus complex conjugate. So this is familiar, right? This is the first part of the pendulum equation. D theta dz equal to ku eta. D eta dz we had it derived before, but also it's in time domain. So it's pretty early when we had even low gain part.
Page 93.
Right. So that's in the scaled version.
Yes, scaled version.
Right. Scaled. It is scaled version. I'm trying to.
Unscaled?
It's okay, yeah. So the small a is related to this e in time, but then you have to go here. I just write it in frequency, right?
Page 91.
91 is probably right. Okay.
Yes.
Right. So yeah, thank you. Yeah, 3.79, right?
Yeah.
D eta dz is this kappa 1. That's the definition of kappa 1 there. And the E tilde is the slowly varying electrical field in time. And remember the E tilde, at the beginning we said E tilde is, if I go all the way back.
It's hard to distinguish kappa and the k with the magnifying glass.
Sorry?
Kappa and the k is very hard to
Kappa
distinguish.
and the K, yeah. Okay, yeah.
It was a one-time call. It's Kai, so maybe can't go back.
Okay.
You need new
We
glass.
we constantly run out of variables. Yeah. So So this is remember this, right? So this, and then there's several. There's E nu tilde, but then E nu tilde is E I delta nu k u z times E nu. If you put that in, this whole thing is E I delta nu theta. Do you follow? You take this definition, and then there's and then we have this definition here. This two combination, you see this two combination will give you delta nu k1z minus ct plus kuz, which is theta. Okay, so that's why That's why this is written in this way. Because now we do everything in frequency domain, so that's why we need this step. Okay, now, okay, with this okay, plug this into here. So put this in here, put this to here, put this to here. So we have df dz plus df d theta 2ku eta plus df d eta kappa 1 d nu di nu theta d nu plus conjugate equal to 0. Okay, so put this in here, okay? Now we say, okay, remember, we slowly transform everything to frequency, but f is still in time, right? We still need to transform f in theta. Now we transform f back into the frequency. Oh, okay, okay, so the way, okay, oh, okay, so there are several, okay, so let's see, now f nu, remember f nu is 2 pi d theta e minus I nu theta f, okay, so that's the definition of f nu. Now, okay, now let's apply this operator to this whole equation here, right? We want to Fourier transform. So the first one, if we have Fourier transform, if I apply this to here, I would get so. Okay. What I'm trying to say is so this f is f nu I theta nu. And this is the inverse. So if I put a f in this form in here, so I have I will have d nu di nu theta df. So f in theta is f in frequency times this okay. If I put this into here, I have df nu dz. Now df d theta. So if I put a f in here, df d theta is just bring this I nu down, right? Mm-hmm. Yeah. So this will be this will bring down I nu f nu. Okay. So put this term corresponds to this. Put this here, I got this. Put this here to here, I got I nu. Now the third one, if you put this here, okay, in here, okay. So we are before I should say this earlier, is now. This term here. This has the electrical field here, right? And we assume now we make this is this continuity equation. If you put now we make this linear approximation. We assume we are looking for the change in f. That's linear that's a linear in the electrical field. So by making this linear approximation, we say this in here, the f here is given by its average distribution. So just trying to make this clear. This one exactly is a nonlinear sort of nonlinear velocity equation. It's not easy to solve, and later we talk about how we can do it in a quasi-linear approximation. But in this linear approximation, we say this is small, and the E itself is also small. So then this has a large, F, remember, has two terms. F that's why we separate. F has a smooth part, which is a large part. This is a small part. So in this here, because it's already this is already time a small parameter. So all I need is keep the large part. By keeping the large part, so I'll have plus. Instead of F, I just write this V here. That's a large part of the distribution. Okay. So F, the large part is a smooth part. So this is already a linearized. So this is equation 1. Linearized equation 1. And then we have this same thing here. Okay. So if you now that it's all in this form. Now if you do now you can get rid of this Fourier transformation part. So what's left is and there's a top of one, I think. Right. Okay. So what's left is df nu dz plus I nu f nu equal.
You need more. You need to there no.
Sorry.
2ku. The second term. No. Over there. The current. Second term. Yeah, there.
Here.
Next.
Here.
Yeah, there. I nu 2ku.
No, I don't have 2ku.
Above there. Top equation, second term.
Here. This is
That's simple.
this is one. Yeah.
So,
Top row, second term.
Top row.
yeah.
Oh yeah.
That's-
Here.
that's
Yeah.
true.
I lost this one here. Sorry. Thank you.
By this reason.
Right. I lost this one. Yeah. Okay. Thank you. So dv d8. Okay, right. So this here I have to carry also carry here, which is okay. Right. Yeah. Thank you. Yeah. Okay. So this is the linearized this continuity equation, and let's think maybe. So now we have two variables, so f nu and e nu. There's this equation, right? Continuity equation, or velocity equation. The Maxwell equation is here. Okay, so we have two unknowns, two equations. So we're set up to solve them. Okay, any questions? Maybe we take a break here.
Coffee break.
Yeah. How long is a typical break? 15 minutes or 10 minutes?
10 minutes.
10 minutes?
10 minutes is short.
Sure.
And that's a code.